Today we're covering angular momentum and angular impulse, one of the most powerful ideas in rotational motion. This topic explains why figure skaters spin faster when they pull their arms in, and why planets stay in orbit, and how collisions work in rotating systems. We'll define key equations and apply conservation laws, and solve some physics problems step by step. So let's start off with what is angular momentum. Angular momentum measures how hard something is rotating. So, for a point mass, we have the general form L is equal to RP, and P, which is momentum, is just equal to R equals mv, so you can just rewrite it as the simplified form. Now for a rigid object rotating about a fixed axis, you have the formula L is equal to the moment of inertia times the angular velocity. So just to label our variables, L, angular momentum. We have I as the rotational inertia or moment of inertia. Angular velocity. And here, this is just our momentum again, and this is measured in kilograms times meters squared per second. R is the distance from axis, and that is just your momentum. So now let's talk a bit about angular impulse. It measures changes in angular momentum. So that's going to be tau times delta t, which is delta L. This is the rotational version of the translational version of F delta t is equal to delta p. Now onto the conservation of angular momentum. We have if the net external torque is equal to 0, that means the angular momentum is conserved. So that means that L initial is going to equal to L final. Or you could represent this as I initial is equal to inertial initial is equal to inertial final times WF. And when does this occur? When does conservation of angular momentum occur? This happens when you have no external torque. The pivot force the pivot forces act at the axis, and also the internal forces cancel. So if there's external torque, you cannot have that. So that would be things you can't have are no external torque, aka friction, and FA, applied force, at a distance. Those would not allow for conservation of angular momentum. Now let's practice some problems in order to exemplify these ideas. So we have problem 1 about a figure skater. A skater spins at 2 radians per second with arms extended. When she pulls her arms in, her rotational inertia drops to 1/4 of its original value. Find her angular speed. So from this, we know to use the conservation of angular momentum. And as we just learned, the conservation of angular momentum is up here, is Li is equal to Lf. The angular momentum initial is equal to the angular momentum final. And we know this is true because we know that there is no external torque. And again, the pivot forces are acting at the axis. When we have this figure skater, she's going to be spinning in a circle like this. She has her arms out, and then so her feet are like this, and then her arms are in. So this is final, and then this is the initial. So when her arms are out, she spins faster, and then when her arms are in, she spins 1/4 of that. So that means you can rewrite the L's with the formulas that we know for angular momentum. I is initial, W initial, IF, WF. Now substituting our values, we have I times 2 is equal to 1/4 I times the angular velocity final. Solving, we have the angular velocity final is 8 radians per second. So what this means is that a smaller rotational inertia will give you a larger angular velocity. Now let's move on to another problem. Let's say we have the angular impulse. A constant torque of 4 newtons per meter acts on a disk for 3 seconds. The disk starts at rest. Find the change in angular momentum. Feel free to try this problem yourself if you want. So we're going to start off with the formula for angular impulse. So this will be tau torque times the change in time, the time interval, which is equal to the change in angular the change in angular momentum. So plugging in our values, we have 4 times 3 is equal to delta L. So then we have the change in angular momentum is just 12 kilograms times meters squared per second. So those are the units that are used for angular momentum. Now let's move on to our next problem. A clay blob of M hits and sticks to a rotating disc at radius r. Find the new angular speed. So this is our disc, and the disc is currently rotating. And it has this radius, so our blob is going to be there. So what's the new angular speed? So we know that angular impulse is equal to torque times change in time. Change is equal to change in angular momentum. So, we don't need that. We think about, is there any external torque? There is no external torque. Therefore, we know angular momentum is conserved, so we can use that principle. But we don't need to here, really. We can just write the initial momentum, which is mass times velocity times the radius, which we get from P is equal to mv. But remember that up here we have this form for a point mass. This is a point mass. So let's actually bring this formula down here so we remember. This was a point mass, so you actually use this formula, this point mass, because it's just a blob of clay. So we have this for the initial, and then we want to write the final. So the final, we know that because when two things stick together, two masses stick together, they become one. So you can write the mass as a sum. So you have I disk plus mr squared times wf. So that's the inertia of the disk plus the mass times the radius squared. So now solving this, we want to just get wf, so you just divide that by I disk mr squared. So we get mr mvr divided by I disk plus mr squared. So to continue on that explanation, the clay blob will move linearly when you throw it. It's going to be a straight line, but it still has angular momentum about the disk center. So then from that, well, earlier we can write that we have angular momentum conserved, so Li is equal to Lf. And this was a perfectly inelastic collision again, because we had this one mass that was, because they combine, it becomes one mass. And then we just have the definition of the moment of inertia, which is a sum of the masses times the radius squared, or you could integrate that. And for this, we have a point mass, which is just the moment of inertia is equal to mr squared. So you add the inertia of the disk plus the mr squared, and then the disk would be 1/2 mr squared. You could actually substitute that in there, but it's fine. So we have these, and then that is going to be your total inertia. So that will be your total angular velocity. So let's continue on with writing some of the key equations that we just used. So some things that you should equations forms that you'll need will be L is equal to LW for angular momentum, and this is for rotating rigid bodies, when you're rotating rigid bodies. And then when you have angular momentum but for a point mass, you have L is equal to R mv, and then this is used for particles and for collisions. Now if you have angular impulse again, or angular impulse, this is for torque over time. Now conservation of L is Li is equal to Lf, no external torque. And when you have angular momentum, we can actually just add this over here. It's fine, and it's a little redundant. So, and for rotational collisions, you can use the form again, Li is equal to Lf for the example we just used, clay, disks, and impacts. So let's continue with some more examples. A point mass M moves with speed v in a straight line. It passes a pivot point at a closest distance d. Find the magnitude of angular momentum of the mass about the pivot at that instant. So there's a mass and it's moving with v, but it passes through here. So we want to find it at this instant. So we want to find L at this instant. How do we do that? We know the angular momentum for a point mass, the formula is L is equal to RP sine theta. And if you're wondering where this formula comes from, it comes from the definition of angular momentum. So we know that L, the vector L, is equal to the vector R times P. It's the cross product, where R is the position vector from the axis or the origin to the particle, and also P is the same thing as it's just momentum. It's also written as, it's just linear momentum. So this is the starting point, and then everything else comes from here. Let's actually move this down a little bit so we can finish fleshing this out. So this, next we have to find the magnitude of the dot product. So we know the dot product is A cross B, which is AB sine theta, where theta is the angle between vectors. So applying this to angular momentum, we have L is equal to R cross P. That's equal to RP sine theta. So that's the formula we're using. And only the perpendicular component of momentum contributes to rotation. So it's actually LRP perpendicular, which is equal to RP sine theta. Because when you have parallel momentum, you have no rotation. And actually, when you have perpendicular momentum, you have max rotation. So this formula matches because we know specifically for circular motion, right? We know that in circular motion, momentum is just equal to mass times velocity. V is just going to be R times the angular velocity, and theta is going to be 90 degrees. So then you have L is equal to R times mass times velocity, which is equal to mr squared times angular velocity, because you can plug in, just so that as R is equal to RW, you plug in V is equal to RW, V there, then you just get. And also, since we know that I equals mr squared for a point mass, then we know that L is going to be equal to the inertia times the angular velocity. So all this is consistent. And this formula, let's actually just box this together. So we know this is just for that formula derivation. This lets you handle collisions, particles, and non-circular motion as well. So we had L is equal to RP sine theta, right? So, but we know that when the particle is closest to the pivot, well, that's when you have the radius is equal to D. And then that's when you have the momentum is perpendicular to R. So then sine theta is equal to 1. So that means you have the angular momentum is equal to D times mv. And then that's where you just get your final expression. That's your answer. Now let's do a problem up here. A uniform disk of rotational inertia I spins at angular speed initial. A ring with inertia 2I is dropped onto it and sticks. Find the angular speed. So this is a disk, right? the disc is like this, and then it's spinning at this speed. So a ring is dropped onto it. So let's say this is the dropped onto it ring, and because it's a ring, it's like this. So now they stick, and if they stick, you know that it's perfectly inelastic, and you also know that you can use conservation of angular momentum with changing inertia. So let's check for external torque. There's actually no external torque, which is why we can use this. So therefore we can write the initial angular momentum is Li is equal to the inertia times angular velocity squared initial, as is from the formula. And the final rotational inertia is just going to be the inertia plus 2 times the inertia, because that's where we get this from. That's 2 times the inertia. And then you get 3 inertia. So then the final angular momentum is going to be LF is equal to 3I WF. Now, if you set them equal to each other, you have I, angular velocity initial is equal to 3I, well, you have from here. And this is because we set from the conservation angular momentum L initial is equal to LF. And this was just here. Yes. So 3 times WF. Let me finish writing this expression. Now we just want WF. So that's just going to be W initial over 3. So that is going to be your solution. Now let's move on to our next problem. A wheel initially has angular momentum of positive 6 kilograms times meter squared over second. A torque acts for 2 seconds and reverses the direction of rotation, so the final angular momentum is negative 4 kilograms times meter squared over second. Find the average torque. So what we need to know is that angular impulse has sign and direction. So what's the equation for angular impulse? Well, this is torque times delta T is equal to delta L. Now the change in angular momentum, this is LF minus L initial, which is negative 4 minus 6, which is just negative 10. Now solving for torque, we have torque is equal to delta L over delta T, and torque is just going to equal to negative 10 over 2, so therefore it's just equal to negative 5 newtons. So times meters. So what does negative torque mean again? It doesn't mean that it's like going away or back. It means the torque is opposite the initial rotation. Now let's move on to question 4. A particle of mass m moving at speed v strikes and sticks to the edge of a disk of radius r and inertia I. The impact is tangential. What does tangential mean again? Well, it means at 90 degrees. So it strikes and it sticks to the edge. It hits it at 90 degrees. It touches the mass only at one point. So you can imagine that's the axis of rotation, that's the center, and then that is 90 degrees. So this is the mass. So actually just draw the mass like in a different color. And then this is at 90 degrees. So how do you get angular momentum? Well, angular momentum, you can get it from the linear momentum. So what is the initial? So the Li initial is equal to R times P, and that's just going to be your radius. Well, we just have here, we're going to have radius of that and your inertia. So your P is just, we can rewrite momentum as mass times volume, which is the linear momentum, angular momentum. So now we want the final angular momentum. So that's going to be I plus mr squared times angular velocity final. So now using the idea of conservation, we have mvr is equal to 1 plus r squared times the angular velocity final. Now we just want angular velocity final, so we're just going to divide. So we have mvr divided by I plus mr squared as our final solution. Okay, now let's move on to our next problem. A rotating platform experiences a frictional torque. Which quantities are conserved? Angular momentum, rotational kinetic energy, both or neither? So what you need to know is you need to know how to identify external torque. Is there external torque? Well, we know friction provides the external torque. So therefore, we know that angular momentum and also rotational kinetic energy, these are both not conserved because of the external torque. So therefore, we know that that's our answer. So therefore, neither of them are conserved. Neither. Okay. A disk rotates freely. Let's go to our last question. A disk rotates freely about a vertical axis. A particle lands on the disk and sticks at radius r. The particle moves radially inward. Does the particle contribute angular momentum before sticking? So it is rotating freely about a vertical axis. So your axis is going to be like this. It's going to land and stick at the radius r. And the particle moves inward. So let's say that the particle first hit here, like initially, and then it's like traveling inward. Okay. It's traveling like inward, right? Does the particle contribute to the angular momentum for sticking? Well, what does angular momentum depend on? It depends on perpendicular distance, not the speed, right? And we know that from the equation for angular momentum, which is L is equal to RP sine theta. And also, we know that velocity is radial. So, a little bit more is like, the velocity is radial. And what does that mean? Along the radius, aka toward or from the center, which is the axis, the object is moving straight inward or straight outward, not sideways around the circle. So that would mean like it's moving straight towards the center of the circle. And we also know that the p vector is parallel to the r vector. And if you're aiming at the center, you're creating no tendency to rotate. And like some examples to illustrate this, is like when you push toward the hinge, the door doesn't rotate. And also when you push perpendicular to the door swings open. So think like your radius is nothing when you're pushing at the hinge, but when you're pushing perpendicular to the door, away from the door, like further away, it swings open. So radial velocity is like pushing at the hinge. in this analogy. So that's why L is equal to 0 here, because the theta is equal to 0 degrees. Sine theta is equal to 0, so L is equal to 0. And even objects can have 0 angular momentum that are moving, even moving objects. So even all right, that's it. Thanks for watching.